In this video, we are looking at concavity. So we've seen that locating the intervals on which a function increases or decreases helps us to describe the graph. Now in this section, we're going to see how locating the intervals on which f prime is increasing or decreasing can be used to determine where the graph of f is curving upward or curving downward. This upward and downward curve is called concavity. So we're going to let f be a differentiable on some open interval I. We're going to say that the graph of f is concave up when f prime is increasing, so when the derivative is increasing. And it's going to be concave downward if the derivative is decreasing. Okay, so let's look at a graphical interpretation of concavity. So here, f is differentiable on some open interval. If it's concave upward on I, then it means that the graph of f lies above all of its tangent lines. So if we look at tangent lines, tangent line, tangent line, tangent line, tangent line, tangent line, they're all below the line, okay? So the graph lies above all of its tangent lines. Now what about one that's concave down, right? This means like the bowl is upside down. If we draw tangent lines, they're all above the graph, okay? So to find these intervals where the graph is concave up or concave down, what you'd need to do is find the intervals on which f prime is increasing or decreasing. Okay, so let's look at this. 1/3 x cubed minus x. We know that it's concave down on the interval from negative infinity to 0. Oh, that's not 0. To 0, right? Because we're talking about the x values. We know it's concave down here because if we take the derivative x squared minus 1 on that interval, if we plug in a test point on that interval, we'll get that that's decreasing, right? It starts really high and then it's getting smaller and smaller and smaller and smaller. Okay? We can also see that the graph of f was concave upward on the interval from 0 to infinity, because from here we started low and we're getting higher and higher and higher and higher. So our slope is actually increasing. So our derivative is increasing. So can we test for concavity? Absolutely. We've already shown that, okay, the first derivative test let us find when the function f is increasing by checking out the first derivative. So if I'm looking for f prime to be increasing, can I not just take the derivative of f prime, which would be the second derivative of f, and determine where it's increasing, or where it's positive and negative, to determine whether the first derivative is increasing or decreasing? So that's what the second derivative, one of the second derivative tests, is to apply that exact thing. Take the first derivative and do what we did with the original function. So if the second derivative is positive, then that means it's concave upward, because that means that the first derivative is increasing. If the second derivative is negative, or less than 0 for all those x's, then that means we're concave downward because the first derivative is decreasing. So to apply this, what we need to do is locate the x values where the second derivative equals 0 or the second derivative does not exist. Right? We're treating this just like we did the first derivative. These are gonna be like the critical values, right? So these are the second critical values. Now we're gonna use these x values to determine those test intervals and then test the signs. It's the exact same thing, we're just taking it the next step. So the first derivative test lets us determine whether the function is increasing or decreasing, thus finding the maximum min. This test, second derivative, we're going to be able to determine whether the first derivative is increasing or decreasing, thus do we have concave up or concave down. So what we want to do is we want to look at this problem and say, all right, let's determine the intervals on which the graph of this is concave up or concave down. So first thing we have to do is notice it is continuous on the entire real number line. X squared plus 3 can never be 0, so there's no value that's being excluded. All right, so that's the first thing. Next, let's find the derivative. Well, let's start by just rewriting it. Instead of trying to do quotient rule on it, let's rewrite it as x squared plus 3 to the negative 1. This is going to make it a little bit easier, right? So when we take the derivative using chain rule, we bring the negative out front, decrease by 1, and then take the derivative of what's inside the parentheses. So if we rewrite this, negative 6 times 2x on the top, the x squared plus 3 squared is going to go to the bottom. Now we do have to take the derivative of this, and we do have to use the quotient rule. We don't have to. We could use the product rule by rewriting it, but honestly, 6 of one, half a dozen of the other. Really, let's just do low d high minus high d low over low low. So low x squared plus 3 squared, low d high is just negative 12, minus high d low, which is 2 times x squared plus 3 times 2x, right? Chain rule, we got to bring the 2 out front, decrease by 1, and then take the derivative of that all over x squared plus 3 squared squared, right? Don't forget to do the squared squared. So what does that give us? Something that looks like this. Excuse me. So we simplify this down. I'm going to leave this to you. Pause this. See if you can't simplify this down. I hope you paused it. Did you pause it? Hope so. Here it comes. All right. So if we simplify that, we're going to get 36 times x squared minus 1 over x squared plus 3 cubed. Now, remember, since this is the second derivative, we want to set this equal to 0. So if we set this equal to 0, then I don't care about the denominator. I only care about the top. 36 can never be 0, so x squared minus 1 equals 0 means that I'm going to get x equals plus or minus 1. All right. Now, because the derivative equals 0 when this is the case, and f prime or f double prime is defined everywhere on the entire real number line, because this can never be 0, right? Because x squared plus 3 is always going to be positive. Then all we need to do is set up a test interval from negative infinity to negative 1, from negative 1 to 1, and from 1 to infinity. So we're going to do our number line. We're going to use negative 1 and 1. We know we can go from negative infinity to positive infinity. We take a test point, and we're going to plug it in to the second derivative. So if we do that, we test negative 2. We determine that negative 2 is actually positive, which means it's concave up. If we pick 0 between negative 1 and 1, we plug in 0 to our second derivative. We get that it's actually negative, so it's concave down there. And then plugging in x equals 2, we get that f double prime of 2 is indeed positive, thus we are concave up. So you can see this graph here. We went from concave up, all right, all of that is concave up. I'm sorry, concave down. Concave up here, right? Then we went concave down, and then we went back to concave up. So the function is continuous on the entire real number line. So when there are x values at which the function isn't continuous, the value should be used along with all the points that gave us f double prime equals 0 or f double prime doesn't exist to form those test intervals. We will need to go back and use the undefined points as critical points. Okay, this is a difference between first derivative and the second derivative. So if you have any questions about concavity, please just shoot me a reminder or ask questions in class.